One of the other applications we have, which is not as familiar to us being that we live in, Dallas, which is a landlocked city, is nautical bearings. So whenever you're driving ships and boats, this is the sort of stuff you would use to talk about the directions that you're headed, especially like on boats, maybe even flights like pilots. But again, we live in a landlocked city, so this is not going to be as familiar to us as probably it is the rest of the things we've done. So we're going to talk about bearing. Again, that's what it's called when we're talking about the angle with which our boat is turning or stuff like that. There's two ways to talk about bearing. So the front page is one of the ways to talk about bearing. The back page of this is going to be your second way to talk about bearing. They will be given to you in both ways, so you need to be able to talk about bearing in both ways. But when I'm talking about bearing, I'm talking about the angle in a clockwise direction from due north, which means we're not talking about a standard looking angle. Our standard angle goes from the x-axis counterclockwise, but a bearing angle goes from north in a clockwise direction. So this is different. So if I said you're on a bearing of 32 degrees, I'm talking about this angle right here. You would face north, then shift yourself 32 degrees, and that's the direction you're heading. If I say you're on a bearing of 164 degrees, boom, you'd go from north, turn 164 degrees almost all the way around, and then start walking. Same thing for 229, and same thing for 304. So it's always from due north. So it's like we're looking at a compass on a map. So let's see what kind of question we can get from this. It says, radar stations A and B are on an east-west line. So flat line. We'll make north up and east-west side to side. They are 3.7 kilometers apart. Station A detects a plane at point C on a bearing of 61 degrees. Station B simultaneously detects the same plane on a bearing of 331 degrees. We're going to find the distance from A to C. So I've drawn this picture for you so you can see what this means. Here's station A, here's the airplane. We're on a bearing of 61 degrees. So from north, that means that this angle is 61 degrees. For station B, it says the bearing is 331. So we're going bloop all the way around here. That's how they're seeing the airplane. What happens is we create this triangle between the east-west stations and the airplane. And it's a right triangle because of the following reasons. If this is a right angle, this is 61 degrees. How did I write down 29? Yeah, 90 minus 61 is 29. So this little piece to finish this right angle would be 29 degrees. Same thing here. If this is 331 degrees, it's like there's a right angle here. How did I get 61 degrees? Yeah, this takes a little bit of thinking. So if I just don't draw this on here because you're going to get confused. So this is 90, this is 90, this is 90. So 270 of the degrees are outside of my circle. If I do 331 minus 270, what do you think I get? 61. So the angle inside the triangle is just 61 degrees. Okay. Cool, cool, cool. All right, so if I take this triangle, and I'm actually going to draw it differently so we can look at just the triangle and not all of the bearing markers. This is what I would have you write down. Okay. Here's my right angle. This is the plane, which is point C. If I'm shifting this graph to make it look like this, that means that this is station B, and this is station A. I know that angle A inside the triangle is 29 degrees, and angle B inside the triangle is 61 degrees. So I've taken the bearing problem, and I've now made it a simpler right triangle. I also know that the distance from A to B is 3.7 kilometers. It wants me to find the distance from A to C. So my goal is to figure out this distance right here. There is an easy piece of trig that we're going to be able to use to find that side length. We know this angle. We know this hypotenuse. And I want the opposite of this hypotenuse. What trig function can I use? I just said it. We can do the sine of angle B, 61 degrees, and set it equal to the opposite, which I do not know. I'll put an X there. And the hypotenuse, which I do know. How do I solve for x? Multiply 3.7 onto both sides. So in my calculator, I would do 3.7 times sine of 61 degrees. Fair warning, dual credit, or not, y'all are dual credit. What is my class before this? AP Pre-Cal has used the calculators today and set them all in radian mode. So you have to make sure you are switching this back to degrees, especially for this class, because right before you, they're using radians. But when we do this, x equal to 3.7 times sine of 61 degrees, you get that purple side length x is how long?
What do you want us to round?
4 decimals, please. 3.261 kilometers. Very good. Now I have a question for you. Because I just did it in my head without saying it out loud, and I know that was not smart. How do I know that this is a right triangle? Well, I wrote that there. But when we were finding this, how did I know I could use right triangle trig? The only information I was given was 61 degrees and 331 degrees. What's 29 plus 61? Which means the third angle has to be what? 90. So I did skip that in my brain because I knew that they would add to 90, which means the missing angle is 90, but you do need to verify that actually makes a right triangle. Otherwise, we're going to use trig we learn in other chapters. But this one will be a right triangle for now. Yes?
So you know how the B is 61 degrees?
Mm-hmm.
Is it just like if you didn't have the other side, the A, could you say it's like equal because the 61 has that?
This one?
Yeah.
Technically, yes.
Okay.
But I wouldn't guarantee that happens every single time because it especially won't happen when this is a right triangle. So do the math first.
Okay.
But yes, because it's a right triangle in these specific problems that we've picked today. But yes, good eye. Any other questions about this one? Drawing the image is the hardest part because, again, we're not used to bearing. We don't drive boats. We don't drive planes. You could in your future, but not right now. You probably don't. Okay, let's go to the next one. The second way we can talk about bearing is not always in regards to true north. So in this way, I'm giving you 2 adjectives, 2 directions to talk about bearing. You're going to start with a north-south line, so not just north, it could potentially be south, and use an acute angle to show the direction, either east or west from this line. So if you notice, this one is called north 42 degrees of east. So we're going from north 42 degrees east. Right? Okay, let's put a compass on here just in case we don't see this. Okay, north, south, west, east. So we're going to the east side of north, just making sure we got that. Does that make sense? If I say 31 degrees south of east, east of south, you go from the south line 31 degrees to the east. 40 degrees west of south, here's south, here's 40 degrees to the west. And 52 degrees west of north, here's your north-south line, 52 degrees to the west. Yes, so when we're doing this, either north or south will come first, followed by the acute angle that you want to take either east or west. So these are a little bit more complicated if you are directionally challenged, but they give you the same information that the bearing problems on the front did. So in example 2, again, I've drawn it for you so you can see what the example would look like. It says, a ship leaves a port and sails on a bearing of north 47 degrees east for 3.5 hours. Then it turns and sails on a bearing of south 43 degrees east for 4.0 hours. If the ship's rate of speed is 22 knots, which is nautical miles per hour, find the distance that the ship is from port. If you took my class last year, these will sound familiar because we did some problems like this. Okay, here's what the image looks like. The ship starts here at the port and starts, I almost said driving, sailing this direction, which is 47 degrees to the east of north. Do we see this? And they go, and they go, and they go, and they go. And then we turn. we specifically turn 43 degrees south of east. So here's south, here's 43 degrees east of south. And they boat and they boat and they boat and they boat. This question wants to know this distance that the ship is from the port if you were to fly like a pigeon or a bird back to shore. Okay, so the image, difficult to draw, again, if we're just given nothing. But do we see where the 47 comes in? Do we see where the 43 comes in? How come I know this is a right angle? They add up to 90. These are alternate interior angles, so they should be the same number, 47, 47. And since this is 43, 47 plus 43 is 90. So I know that this is a right triangle. We can use our right triangle trig. Here's another problem. I need to know these side lengths because I'm not given enough information to use right triangle trig the way we have with sine, cosine, and tangent. I'm actually going to need to use side lengths to determine the missing side length. Where did this image get 77 nautical miles from? Because it's not in the little blurb. The speed, it says that the ship's rate of speed is 22 miles per hour, nautical miles per hour. So that means that my distance, physics friends, is rate times the time. So for that first distance, so this is the distance 1, I'll make that red so we can see that's what I'm doing. Distance 1 is 22 nautical miles per hour times how long? How long were we first traveling? 3.5, which gives me 77 nautical miles. For the second distance, which is my blue distance, distance 2, I'm still boating at 22 nautical miles per hour, 22 knots, but how long am I traveling that direction? 4 hours, which is where I get the 88 nautical miles from. I keep missing the U in the word nautical. So if I were to redraw this triangle for myself, just so that it's simple to see, I'll make my right triangle look like this because I always do. Okay. From the port, which we'll call this the port, from the port to the turning point, that was 77 nautical miles. From that turning point to where the boat is right now, that was 88 nautical miles. How do you find this missing distance when you're given two sides of a right triangle? Yes? Pythagorean theorem, which is the same as the distance formula technically. So if we solve Pythagorean theorem, we'd be doing a squared, can I get the colors right? A squared plus B squared equal to the C squared that I've highlighted in purple. We plug in what we know. We know that A is 77. We know that B is 88. We solve for C squared by taking the square root of that number. We'll fast forward through the math because I trust us to type it in a calculator. 77 squared plus 88 squared is 13,673. So if you take the square root of that, that means that the C value, the distance from the boat to the port, is 116.9316 nautical miles. So sometimes when you're doing these bearing problems, like on the front, you'll use sine, cosine, or tangent to find one of the missing things. Or you can use the side lengths, especially if you're given easy distance, rate, and time to do Pythagorean theorem. Another application we have from the textbook is about what's called the subtense bar method. I've never been a surveyor before in my life, so I don't actually know like physically how this works, but it's a tool that surveyors, those people that stand on the side of the highway, they look like they're looking through like a you know what I'm talking about? Does a surveyor. So this is what they do. I've never done this in my life, so whatever. Anyways, they determine a small distance between 2 points, P and Q. So here's P, here's Q. The subtense bar with length B I think that should be a D. No, B here. B is centered at Q and situated at perpendicular to the line of sight between P and Q. So these are perpendicular. Ooh, look, a right triangle. Angle theta, the whole thing, is measured, and then the distance D can be determined. We're going to find that distance D when theta, the whole thing, is 1 degree, 23 minutes, 12 seconds, and the B value is 2 centimeters. Well, let's first of all get this angle in terms of something we can type in the calculator. If I was converting 1 degree, 23 minutes, 12 seconds into degrees only, I would do 1 plus 23 times 1 over 60 plus 12 times 1 over 3,600. Yeah. And 12 over 3,600. I don't know why I wrote it like that, now that you're saying that. I don't think I've ever written it like that before, but here I am. If we throw that in a calculator, again, I'm trusting you to be able to do some math like that, we would get 104 divided by 75 degrees, and we're going to leave it like this because it's a string of decimals, and I don't want to lose specificity of this number, so we'll leave it as a fraction. Okay. Now this that we just found is theta. Theta is this entire distance for both the top right triangle and the bottom right triangle. So if I only want one of those triangles to find D, which is this guy right here, what will be theta for me? If the whole thing is this, what would half of it be? Is basically what I'm asking. To take half of a fraction, you just take half of the top number. What's half of 104? 52. So this is 52 over 75 degrees. Okay, we're almost able to do some trig. We just need one more side length. I'll tell you right now, you can find this side length. How did you get 1? Yeah, that side length, if you look at the image above, is B divided by 2. And our problem says that B is 2. So 2 divided by 2 is 1. So I'm getting that from here and here. So we have a right triangle, we actually look like a right triangle, where we know an angle and we know a side and we want one more side length. What trig function relates the sides that I have highlighted to that angle? Tangent. If I write a tangent trig function, it would say tangent of this angle measurement, 52 over 75 degrees, would be equal to the opposite over the adjacent. Let me use the right letter. This is D. Okay, how do we solve for D here? So yes, if we were showing all of the algebra steps, you technically would multiply by D on both sides. So you'd have D times the tangent of 52 over 75 degrees equal to 1. And then yes, to get D by itself, you would have to divide both sides by that tangent value. So it'd be 1 over the tangent of 52 over 75 degrees, which is, I ran out of room a little bit. That's something we can throw into the calculator. Again, trusting you to be able to do this in degree mode. Make sure your calculator's in degree mode. This would end up being 82.6341 centimeters of the value of D. What?
Because it's so big.
Yeah.
Compared to the rest.
No. Because it's the longest. If you notice, that's like the longest thing. If this is 2, that's based on the image, should be pretty long. Are there any questions about that one? The main goal with these applications is to make sure you can set up a right triangle. Once you understand the problem enough to set up your right triangle, it's easy trig that we've been doing. So setting it up, probably the hardest part. The next question says, how much change would there be in the value of D if theta measured 1 second longer? Okay, so we're changing theta. This time the theta, the whole thing, is now not 1 degree, 23 minutes, 12 seconds. It's 1 degree, 23 minutes, 13 seconds. So if we make that into a usable degree value, again, this would be 1 plus 23 over 60 plus 13 over 3600. Beep, beep, bop. That's a calculator question, and you're going to leave it as this ugly fraction because the decimal you'd have to round, 4,993 over 3,600. If you rounded it to a decimal, you'd be losing some of the specificity of the number. Your answer won't be as accurate. We've already figured out the math, though. We already know that our triangle here is going to have the value D. Oop, highlighter, please. And it's going to have a B value of 2, of 1. That hasn't changed, same as before. But I don't want to use the same theta I just wrote down because that's the whole top and bottom triangle. So we're going to divide it by 2. Since the top number is not divisible by 2, you end up with an even uglier fraction, 4,993 over 7,200. That was multiplying the denominator by 2, since the numerator is not divisible by 2. Okay, this time we're going to do the tangent of this wild fraction, degrees, equal to 1 divided by our length d. We already saw that when you're solving for d, you basically flip-flop the sides of d and the tangent, which if any of you are in physics and y'all still do the triangle for distance, rate, and time, same idea. This means that the distance would be equal to 1 over the tangent of 4,993 over 7,200 degrees, which if we fast forward again, because again, we can type stuff in a calculator, we'd get that that distance is 82.6176 centimeters. But that doesn't answer the question, because the question says, how much change would there be? So comparing this value to this value, how much change is it? 0.0165 technically centimeters shorter. So our new one is shorter, or smaller number than our old one. So that's the change. Correct. Yeah. Okay, this last problem is my favorite. You'll probably guess it. Use your small handwriting for it. It says Francisco needs to know the height of a tree. And instead of measuring it, what he does is he goes from a given point on the ground. He finds that the angle of elevation to the top of the tree is 36.7 degrees. So he's looking up, measures the angle of elevation. Check. And then he moves back 50 feet. And he looks up to the top of the tree again, and he gets that this angle of elevation is 22.2 degrees. We're going to find the height of the tree to the nearest foot. So let's look at our image here. The first time he looks up at the tree, this is the angle of elevation. He's at some distance away from the tree, it didn't tell us. Then he walks 50 feet further back and looks again. We need to find this height. The problem is, we don't have enough information just with those two triangles that we were given to solve this problem. If I go for the bigger triangle, this is 22.2 degrees. I know that the height is h, that's what I'm looking for. But what is the distance from the tree that he's standing? 50 plus something, and that something is x. Because he's 50 feet beyond that first measurement. If I go for my smaller triangle, h is still my height. Pretend those are the same measurement. My drawing skills are not great. This angle right here is 36.7 degrees. What is the horizontal distance? Just x. Neither of those have a full side length for me to be able to use to find height in a regular trig problem. So we got to get creative. Let's write both equations right now, the one for the big triangle and the small triangle, and see what happens. If I pretended like I actually knew this value, to find height, I would probably use tangent, because I know the opposite and I know the adjacent. So I would set this up and I would say, all right, the tangent of 22.2 degrees should be equal to the opposite, which is h, divided by the adjacent, which is 50 plus x. Same thing for the second triangle. I would use tangent since I know the opposite and the adjacent. This would be the tangent of 36.7 degrees equal to the opposite h over the over the adjacent x. Have I lost anybody? I've just set up two trig problems, neither of which I have enough information to solve for. What letters are in both sets of equations? X and h. What would be easier to solve for right now, x or h? H. Let's solve both for h. If I solve the first one for h, I'm going to get that h is equal to 50 plus x times the tangent of 22.2 degrees, because I just multiplied that binomial in the denominator to the other side. If I solve for h in the second equation, I would get that the height is equal to just simply x times the tangent of 36.7 degrees. What are both of these equations equal to? Which means they're both equal to each other. So algebraically, since they're both equal to h, I can do this. 50 plus x times the tangent of 22.2 degrees is equal to x times the tangent of 36.7 degrees. They're equal to h, so they're equal to each other. In that long string I just wrote, what variable is left? X. It's just in two places. If there's only one type of variable in one equation, I can solve it. So let's do that. First things first, this has to be multiplied and distributed to both of these terms in the binomial. So if I distribute that, and yes, you're going to write a lot of stuff on this problem, we get 50 times the tangent of 22.2 degrees plus x times the tangent of 22.2 degrees. All of that equal to the x times the tangent of 36.7 degrees. Let's rearrange some things. Let's put all the x's on the same side. Since there's an x already on this side, can I move this x that direction? Yeah, this whole term right here, I'm going to subtract to the other side so that it moves to the other side of the question, which means now my equation would say 50 times the tangent of 22.2 degrees equal to what was already over there, x times the tangent of 36.7 degrees, minus the thing I moved over there, x times the tangent of 22.2 degrees. No, you cannot combine them together right now because you don't know what tangent of 36.7 minus tangent of 22.2 is, and we're not going to round yet because it would not be helpful for us in the long run. Oh boy. Okay, so now the x's are on the same side, but they appear in two terms. What can I do? Yes, wrong word, right idea. Starts with an F. Factor them out so that I pull them out of both of them so they cancel, which is where your brain was going. But they don't just disappear, they go into the front, and then I open a set of parentheses. This would be tangent of 36.7 degrees minus the tangent of 22.2 degrees. I just yanked out the x and put it in front. It does look like they cancel, but it's called factoring. And then this other side, yeah, it's still there. Okay, we're so close because now we have an x by itself, sort of. It's just multiplied by something. How do I get rid of stuff that's multiplied times a variable? I just didn't hear you. Yes, we're going to divide both sides by that entire parentheses so that I would have 50 times the tangent of 22.2 degrees, all divided by the tangent of 36.7 degrees minus the tangent of 22.2 degrees equal to x. I love algebra. Are there any variables left on this side of the equation? Which means you can throw it into a calculator. Okay, I actually need you to do this one because I didn't write the number down because you'd have to round it. So put it in your calculator and don't press clear. I need it to be on the screen for us to use in a second. Because we're going to get a really accurate number here. Oh, I don't think I'm in degrees. By the way, we should get approximately 60.4968. But don't lose that number in your calculator because we're not going to use this approximate number in our next step. Because remember, the goal here was not to find x. What was the goal to find? The height of the tree. Yeah, we need the height of the tree, and that's solving for x. I need to solve for h. But if you look back up at the top of your paper, don't you have a nice simple equation to solve for h? This guy. What's the only thing I have to plug in here to be able to solve for h? Didn't we just find it? So what we're going to do in our calculators, we're going to use that equation, and we're going to say h is going to be equal to that x value you just found. That's why it's still in your calculator. Multiplied by the tangent of 36.7 degrees. So you still have it in your calculator. You didn't lose it. Just press times tangent of 36.7 so that you have a really, really accurate number. What is the height of that tree?
49.0929.
Exactly. If we rounded that number, you'd probably get an accurate-ish number, like if you did 60.4968 times tangent of 36.7. But if you want to be really specific, which I would love, you're going to use the actual value there and only round at the very end. Don't round in the middle. Okay, whoa. I know you just struggled to write all of that down while I spoke through it. So let's look back through it and make sure we understand the steps. Okay, I first drew my two triangles. Did we hang on through the drawing of the triangles? Okay. Did we hang on through this part right here? This is just setting up regular sine, cosine, or tangent, which in this case is tangent for both triangles. I solved both of these for h so that they had a variable in common. I could have solved for x, but it would have been more complicated. Could have. Okay, so then once they're set equal to h, I know that these expressions are equal to each other, so I just wrote that down. My goal now is to solve for x, but since x was on both sides of the equation, thank you, I had to rearrange my equation. We distributed tangent of 22.2 degrees. We moved all of the terms with x's to the same side. We factored out the x's from both of these terms. And then we divided by the constant in front of x, even though it's like all these tangents. We got the value of x. We put it in a calculator to get a number. But then to solve the actual question here, we took that number and we multiplied it by tangent of 36.7, since I know originally that's one of the ways I could find h. And then I have the value of h. Questions, comments, concerns about this question?
Is this on the homework?
Yes.
Like just one or it's not? Like
I honestly don't remember if it's more than one.
how many homeworks are you doing Tuesday?
Say again?
Probably like 4.
Yeah.
Oh,
Yeah. We're going to do some math today.